I started planning this video because I asked myself the question, what is the natural starting place for a series of technical videos on Python? And eventually I wanted to move into the Python documentation and start explaining specific parts of the Python programming language, but I was wondering where exactly to start. And asking that question took me pretty far back to some basic things, including asking what a machine is, asking what a programming language is. So what I'm gonna try to do in this video is begin by talking about what a machine is, and eventually work my way to the Python documentation and its different parts. And my goal along the way is to give you context so that when you look at the Python documentation, you can understand what it is and why it's segmented in the way that it is and what kinds of things you'll find in the different places. And hopefully you'll also learn some interesting things along the way that are useful as you continue programming in the future. So I'll start by saying a machine is a device that converts energy into useful work. So you've probably learned about simple machines back in high school science class or middle school science class. A pulley is an example. So I have a rope that's connected to a wheel that's maybe fixed into the ceiling, and then the other end of the rope is connected to some object that I want to lift. This machine converts the energy that I put into the rope with my hands into the work of lifting the object upward. And the pulley, this device, allows me to draw the rope toward myself in any direction, and it does the work of pulling this object upward. The pulley converts my energy into useful work. So that's a basic example of a machine. It's not the only machine that we use. We're used to working with much more complex machines, but any machine is going to convert energy into useful work. Every machine is going to offer some finite amount of potential, and I mean potential to perform some function. So for example, a pair of scissors is a couple of wedges connected by a fulcrum, and it converts the energy that I put into moving the handle into higher pressure along the edge of the blade that cuts through a piece of paper, for example. The potential offered by a pair of scissors is the ability to open and close in a certain range, to cut a certain length of paper or whatever else. Now contrast that simple machine with something slightly more complex, like my blender. My blender is able to pulse. I press the button and the blender spins as long as my finger is pressing the button. I can also set my blender to spin at low or medium or high speed. So you could say my blender has 4 different functions, and because of that, it has 4 different buttons. The potential offered by my scissors is different than the potential offered by my blender. Both are machines, but they offer different degrees, different kinds, let's say different amounts of potential. A user manipulates a machine in order to actualize its potential. So the scissors aren't going to cut anything by themselves. My blender is not going to blend anything by itself. The machine requires me to manipulate it to turn the potential that it offers into actual work. I have to take the handles and squeeze them in order to make the scissors cut something. I have to press the button on my blender in order to get it to spin to blend anything. So a user manipulates the machine to actualize its potential. In order to manipulate the machine, the user needs an interface. So the interface on the scissors are just the handle, and that's different than the thing that's doing the work. I mean, the part of the scissors that are doing the work are the blades. The handles are made to fit my hand. That's the part that I interact with. On the blender, the interface is the buttons. I have the pulse button, low, medium, high. That's the way that I manipulate this machine in order to actualize its potential. An interface is a functional representation of the potential of the machine. I'm going to break that down. The interface is a functional representation of the potential of the machine. So we said a machine offers certain potential, some finite amount of potential. The user has to manipulate the machine in order to actualize that potential, and the user manipulates the machine through an interface. So the interface must correspond with the potential of the machine. For example, my blender has the potential to pulse or spin at low, medium, and high. Therefore, it has 4 buttons. Or another example is in my kitchen, I have a Keurig, and the point of the Keurig is to make single cups of coffee. And this is a simple one. It doesn't make small, medium, and large cups of coffee. It only makes whatever amount of water that you put in its reservoir. And it's started by pushing 1 button. So this machine basically has 1 function, make 1 cup of coffee, and the interface is 1 button, and I push that and it does that function. So my Keurig has limited potential, and it also has a simple interface. On the other extreme, the cockpit of an airplane has knobs and buttons all over. It's a complex interface. Why? Because the potential of the machine, the airplane, is great. There are many different things that a pilot can modify as the airplane is flying, or even to get it flying in the first place. And therefore, in order to make all of those manipulations, the pilot needs a relatively complex interface that he can interact with to tell the machine what to do, or to cause the machine to execute functions, various functions, in particular ways. Through this example, this comparison of the Keurig to the cockpit, you can see that there's a relationship between the potential offered by the machine and the complexity of the interface of the machine. When the machine offers greater potential, a greater ability to perform a greater variety of functions in a greater number of ways, the interface has to be more complex in order to allow the user to manipulate the machine in a greater variety of ways. Now let's talk about computers. A computer is a machine that is designed to process logical operations. Just like the pulley, just like the Keurig, just like the airplane, a computer is a machine, but it's designed for a specific purpose, and that purpose is to process logical operations. The job of a computer interface is to allow the user of the computer to determine the logical operations that the computer processes. I'll say that one more time. The job of the interface of a computer is to allow the user to determine the logical operations that the computer processes. The hardware of the computer directly is manipulated by a series of high and low voltage. That's the zeros and ones. But I can't produce that series, that pattern of voltage changes by myself. I can't do that with my body in the way that I can press a button on my blender or turn knobs and levers in the cockpit of an airplane. I need an interface that will do that for me. That interface has to present me with a way to define, to indicate the logical operations that I want the computer to perform, and then the interface has to convert my input into patterns of voltage that my CPU can execute. But this presents a problem. Reconfiguring my computer at the lowest level is incomprehensibly complex. It is many orders of magnitude more complex than configuring an airplane in a cockpit. And for that reason, the interface that I would need to offer me all of the potential that my hardware has in it, that interface would have to be orders of magnitude more complex than the interface of the cockpit. And we can see this if we look back at early computers. The ENIAC was invented during World War II. This was an early computer, and it filled up a whole room, bigger than a cockpit. This computer was programmed using wires and switches, thousands of them. Wires plugged into a plug board in a certain configuration that caused electricity to flow in a certain way to create a certain kind of circuit so that this computer would process a certain kind of operation. It took the operators of this machine days, and it was a team of people. It took them days to reprogram the computer to execute a new series of operations. And the ENIAC had less than a kilobyte of memory. Computers today have gigabytes. A gigabyte is a billion bytes. A kilobyte is 1,000. And so you're looking at something like an order of 1,000,000 times more memory, which means 1,000,000 times greater reconfiguration potential that modern computers have compared to something like the ENIAC. And the ENIAC's physical interface took up a whole room, and it took multiple days to reconfigure. So that kind of physical interface would never work for something like an iPhone, which is so much more complex. If we created a physical interface for modern computers, we wouldn't have the space, we wouldn't have the power, we definitely couldn't carry it around in our pockets. So we need some other kind of solution. One of the ways that we solve this problem is through layers of abstraction, and I'm gonna try to explain what that means. I live in Dallas, Texas, and in Texas we have a lot of Tex-Mex restaurants where I can go and get things like burritos. Imagine that there's a restaurant, let's say it's called Rosa's, and at Rosa's they sell two kinds of burritos, a chicken burrito and a steak burrito, and that's all that their menu has. That's nice because when I go into the restaurant I don't have to think for a long time about what I'm going to order. The problem is there's not much room for me to customize what I'm going to eat for dinner. I don't have very much choice. So if I don't want a chicken burrito or a steak burrito, I have to go to a different restaurant. Maybe they'll let me make some small modifications like adding extra rice to one or adding extra beans to the other, but they're not going to let me recreate the burrito from scratch. It's not that kind of restaurant. On the other hand, I can go to Chipotle, and as I go through the line, they offer me this array of ingredients that I can use to construct my burrito from scratch. I can tell them I want a tortilla or I want a bowl, I want chicken or steak, I want black beans or pinto beans, I want white rice or brown rice, and so on. So this gives me a greater level of control, but it also involves more interaction between me and the worker at Chipotle than ordering a chicken burrito at Rosa's. In this example, Rosa's has created a layer of abstraction above what Chipotle offers me. Rosa's also has ingredients in their kitchen, and potentially they could arrange those ingredients into other kinds of dishes than chicken and steak burritos, but they've chosen not to do that. They've arranged them into chicken and steak burritos, and then they give me a menu. That menu is a sort of interface, and I say, I would like a chicken burrito, and they bring it out, and I don't have to tell anybody what ingredients are inside of it, so it simplifies things for me. Chipotle gives me a lower level of abstraction where I'm more involved in the granular details of constructing my burrito, but Chipotle still does offer me a layer of abstraction. If I wanted to go a layer beneath that, instead of going to Chipotle, I could go to a grocery store, because even though Chipotle does offer me ingredients that I can arrange into a burrito, it doesn't offer me everything that I would need to make a broccoli casserole. If I wanted to do that, I have to go to the place where I get my ingredients, the grocery store. The grocery store offers me a wider array, like hundreds or thousands of things that I can use to make a meal rather than a dozen or so at Chipotle. But I also have to do more work in order to turn all of that potential into an actual meal. First, I have to make a plan. Chipotle's basically given me a plan. Rosa's has given me a very simple plan. Chipotle's given me a slightly more complex plan, but there's still a pathway for me to navigate. Like, they ask me a series of questions. Do you want this? Do you want that? The grocery store doesn't do any of that for me. So I have to make my own plan. I have to decide what I'm going to have for dinner. I have to figure out the ingredients that I need to create that. Then I have to navigate through the grocery store myself, take the ingredients off the shelf, put it into my basket, take it home, wash my vegetables, chop them up, cook everything, put it on a plate, and then I'll have something to eat. So there's much more potential in the grocery store, but the interface, if I can call it that, is more complex, and it requires more labor for me to turn that potential into an actual meal. So Chipotle offers a layer of abstraction on top of the grocery store by taking those components and preparing a smaller array of components that I can then assemble into a burrito. And then Rosa's offers a layer of abstraction on top of Chipotle by not giving me any ingredients at all. It just gives me two choices of meals that I can eat. So the lower I go, the more potential I have. The higher level of abstraction I go to, the less potential there is, but the easier it is to actualize the potential that remains into a meal that I can eat. We address the complexity problem in computers in a similar way. Somebody has to go all the way down and design the hardware, meaning they're creating the CPU. They're creating the control unit that takes binary code out of memory and fetches it for the CPU. They're creating the decoder that converts that binary code into action performed by the CPU. That's complex. It's very low level. It's not relevant to my life. It would be difficult for me to learn. And luckily, I don't have to learn that because people have built layers of abstraction, kind of like Chipotle goes and they do the grocery shopping for me. They cook the beans for me. They season everything for me. And then they put it there in a little container so that I can go and grab it and put it into my burrito. A programming language is kind of like that. Somebody who understands the lower level hardware, the lower level machine code, has created an abstract machine, if you want to call it that. It's a digital machine that's housed in the hardware of the computer that packages logical operations for me. And so remember, the computer is a machine that's designed to process logical operations. The low level hardware provides the basic ingredients for performing logical operations. The designer of a programming language arranges those basic ingredients to perform logical operations that are commonly used. So for example, the hardware itself is not going to execute addition or subtraction for me, but the designer of a programming language knows somebody who's using a computer is likely to need a function that performs addition or subtraction. So they design a machine that achieves addition or subtraction and creates the machine code that goes to the hardware that executes that operation. And then it presents you, the user, with a sort of menu, kind of like Rosa's or kind of like the ingredients at Chipotle, which just looks like a plus sign. If you put a plus sign in your code, that is going to activate this machine that the designer of the programming language has designed on your behalf. And it's not necessary for you to design a new kind of addition, so that's good enough. You don't have to learn the machine code. You don't have to learn about the hardware. You can just use the tool that's already been created for you. But it doesn't have to stop there. Now that the addition operator has been created, somebody else can incorporate that into their own layer of abstraction, meaning they can create a logical operation that does addition and also other things, and they can package that into a function and offer it to you to use without having to know the underlying details. So my point is, one of the ways that we address the complexity of computers is through layers of abstraction. We build logical machines, digital machines, abstract machines on top of the computer hardware, and we make that accessible through something like a computer programming language that is simpler to interact with than interacting with the lower level computer hardware. Kind of like Chipotle makes things simpler for you than going to the grocery store, kind of like Rosa's makes things simpler for you than Chipotle. And the higher you go in abstraction, the less potential that you have, but also the easier it is to actualize the potential that remains. Meaning it's easier for you to achieve something practical and useful because other people have designed machines that do the lower level work for you. So effectively what we're doing is we're building abstract machines on top of physical hardware. That abstract machine has an interface, and that interface is a functional representation of the potential of the abstract machine. But the potential of the abstract machine is slightly less than the potential of the hardware upon which it is built. Then I can build another abstract machine on top of the lower abstract machine, and this higher level abstract machine will itself have an interface, which is a functional representation of the potential of that higher level abstract machine. Specifically, lower level languages like C are closer to the hardware of the computer. They're closer to the machine code that's given to the CPU of the computer. Python is built using C. So you see, we have multiple layers of abstraction. At each layer, there's a new abstract machine placed on top of a layer beneath it. That abstract machine has an interface. The higher we go up layers of abstraction, the simpler the interface is, but the cost is that this machine offers slightly less potential. When you create a program in Python, you're creating a new layer of abstraction on top of the Python abstract machine. And you create an interface which a user can use to interact with the machine that you have built on top of Python, which is built on top of C, which is closer to the machine code that is interpreted by the hardware. So we've covered layers of abstraction. Now we can say a programming language is the interface of an abstract machine. A machine is built, in the case of Python, this machine is built on top of C, and then that machine offers an interface to its users. That interface is the Python programming language. The Python programming language is the way that you manipulate the Python machine in order to actualize its potential. Just like the buttons on my blender are the interface which I use to actualize its potential. Just like the handles on the scissors are the interface that I use to actualize its potential. The Python programming language is the interface that you use to actualize the potential of this Python machine, which is built on C. So now, a question that I've been asking myself is, why is this interface language-like? We call these things programming languages. That's interesting because you're not talking to your computer the way that you would talk to me. If you had something to say to me, first you would have some meaning, something that you wanted to communicate, and then you would find words to represent what you mean, and you would say them to me. I would listen to you, and I would interpret your words so that I can understand your meaning. That's not exactly what a computer is doing. There's nothing in this hardware that understands what you mean when you type code, just like when you type letters and numbers on your keyboard. The keyboard doesn't know what you mean when you do that. The keyboard produces electric signals based on its circuitry that go to your USB port on your computer, at least for me, because mine's plugged into my USB. It goes to the USB port on my computer. At no point does the keyboard know what I'm saying. And so it's interesting that we call a computer programming language a language, but it is language-like. Why is it language-like? It's language-like because computer code consists of a series of symbols and words that are arranged in a meaningful order, and then the Python interpreter, we call it an interpreter, converts that series of symbols and names into, eventually, machine code that's executed by the CPU. That's similar to how when I'm speaking to you, I'm using words, and those words are combined to form phrases and sentences and paragraphs. In other words, they're arranged meaningfully, and then you interpret what I'm saying, and if I'm asking you to do something, then you can go do it. Like, hey, could you please go grab me a black pen? You know what I mean. You can go and execute that instruction. But the computer's not like that. It doesn't understand what you mean. When you write computer code and you execute it, you're initiating a series of physical events that force the computer to execute some function. Just like when I'm playing my guitar, I press a string down using force with my finger. That causes the string that I'm pressing to become shorter, which causes the frequency at which it vibrates to be higher when I pluck the string. And so it plays a different note. I'm not asking my guitar to play a higher note. I'm making it play a higher note with physical force. That's essentially what's happening with the computer. So why is it that we manipulate the computer physically using something that appears like language? Well, I think the answer is there's a relationship between language and abstraction. We've already talked about how layers of abstraction allow us to deal with the complexity of computers by rolling up functions into higher levels with simpler interfaces. Well, language does not become less effective at higher or lower levels of abstraction. You could say language is abstraction agnostic, meaning as long as I'm referring to some real thing, it doesn't matter if that thing is highly abstract or completely concrete. I'm able to name that thing as an object and I can speak about it rationally and communicate meaningfully. Language is no less effective speaking about abstract things versus speaking about concrete things. So I can use language to refer to the very low level parts of a computer, like the hardware, the CPU, the control unit of the CPU, the memory, the machine code, and I can also use language equally as effectively to talk about making characters bold in Microsoft Word by holding the control key and hitting B. The developers of the Python programming language create the Python machine, which is called the Python implementation, from the lower level language, C, and then they make the parts of this machine accessible to users with meaningful labels. That meaningful label might be a plus sign that's associated with addition, or it might be a print function name that's associated with the function that displays output. But the point is that these labels, because the developer designs the Python interpreter this way, these labels catalyze the function that is associated with that label. The plus sign catalyzes the addition operation. The developers could have designed the Python interpreter so that the minus sign catalyzed the addition operation, but that wouldn't make any sense to users. The developers could have caused a random series of numbers and letters that's 12 characters long to catalyze the addition operation, but that wouldn't make any sense to users. What the developers have done is they've caused meaningful symbols and meaningful names and meaningful arrangements to catalyze the functions of this Python machine that they have created. And so then the interface that you interact with is language-like. It's meaningful. It's also complex, kind of like an airplane cockpit or kind of like all of the items that you can buy in a grocery store. But because it's language-like, because it's meaningful, you can remember the way that this machine is structured and command it, even though it's complex. You can manipulate it with relative ease, kind of like you could have a conversation with me with relative ease, even though the arrangement of words that you would speak to me with is complex, probably more complex than the cockpit of an airplane. We humans are able to learn and deploy language naturally. We're good at that. And so this interface that we use to define logical operations for a computer to process has come to be language-like. And that's an amazing thing. So now, what does that have to do with the Python documentation? Well, the two sections of the Python documentation that I spend the most time in are the language reference and the library reference. The language reference describes the so-called syntax of the Python programming language, and the library reference describes the built-in tools and the modules that are included in the Python installation. I'll explain what that means. And I'll explain what that means starting with the library reference. The built-in tools and the modules in the Python standard library are like the tools in a Swiss Army knife. A Swiss Army knife contains many different tools, and each one of them might be used for a different purpose. If you weren't familiar with the tools in a Swiss Army knife, I might write a user manual for you. And in that user manual, I might say, this is a bottle opener, and here are its parts, and here is how you use it. This is a corkscrew, and here is how you use it. This is a nail file, and here is how you use it. These are scissors, and here are how you use them. That's what the Python library reference is. The Python library reference describes each of the tools included in the Python installation, what their parts are, and how you use them. The number of tools that are included in Python is huge. So you probably will not use most of the tools in the Python standard library, at least not for a long time. That means that you're not going to read the library reference from top to bottom. You're going to consult it whenever you need to know how something works. Having said that, it can be useful to review at a high level to see if something catches your eye as potentially useful for whatever project you're working on. If something in the library reference seems useful to you as you scroll through the table of contents, you might want to take a look at that page to understand the tool so that you can put it in your mental toolbox and deploy it whenever it's relevant in your work. Another way of describing the library reference is it would be like writing a description of each of the items on the shelf of the grocery store. The grocery store has many different things that you can put in your shopping basket and take home to cook. If I wrote a book describing each of those ingredients and how they might be used, that would be like the Python library reference. The Python language reference, on the other hand, contains general instructions that you need to know about no matter which of the tools you're deciding to use. So for example, to continue the grocery store illustration, if I wrote an instruction manual that said, when you go into the grocery store, if you don't need very many things, then you can carry items with your hands. But if you need a lot of groceries, then you might want to get one of the little baskets. If you need more groceries than that, you might get one of the push carts, and you can use that no matter what you're buying to carry your ingredients around the store until you're ready to exit. Then after you get your ingredients from the shelves, you go to the checkout. Don't exit the grocery store without paying for your groceries or you're going to have a problem. When you're going through the checkout, you can go to a cashier or you can go to the self-checkout. If you go to the self-checkout, scan each of your items and place them in a grocery bag, and then you can put the grocery bag back in your cart and take it to your car. So this booklet, if I wrote these instructions for you, would give you general instructions for navigating the grocery store no matter what particular thing inside of it you're using. The Python language reference is like that. It tells you the syntax of the Python programming language, which is relevant no matter which built-in tool or module you're using in the Python standard library, or if you're using some third-party library that you've downloaded from some online repository. So let me try to sum this up. We've said a machine is a device that converts energy into useful work. A user manipulates a machine in order to actualize the potential offered by the machine. But the user needs an interface in order to manipulate the machine to actualize its potential. An interface is a functional representation of the potential of a machine, and a machine with a greater potential tends to come with a more complex interface. A computer is a machine that's designed to process logical operations. And at its bottommost level of the hardware, a computer offers vast, incomprehensibly great potential, which would require a impractically large and complex interface if that interface were built physically like an airplane cockpit. We solve that problem using layers of abstraction, which build abstract machines on top of lower level machines. So first, there's an abstract layer built on top of the computer hardware, for example, the C programming language, and then we can build another abstract machine on top of that, like the Python machine, and each one of these abstract machines has an additional interface. So the C machine offers the C language as its interface. The Python machine interacts with that interface and builds a machine of its own and presents a new interface, which is the Python programming language. And then if you build a program in Python, you're building a new abstract machine on top of Python, and you're presenting users with a simpler interface of your own. These interfaces are language-like because language is abstraction agnostic. It is equally as effective at any level of abstraction as long as you're referring to some real thing. And so the developers of these machines and their interfaces, the programming languages, associate meaningful symbols and meaningful words with the parts of these machines that they build, so that you can manipulate them effectively to accomplish useful work. Because these interfaces are language-like, they have a syntax, and in Python, you can learn the syntax by going to the Python language reference. You can also learn about the various tools offered by this machine by going to the Python library reference, and in future videos, we're going to look at some of those things specifically so that you can understand them and use them. That's all for this video. Thanks for watching, and if you found it interesting or useful, please subscribe.